Alrighty, here we are with chapter 17, which has to do with planar kinetics of a rigid body. And so now we're looking at rigid bodies now. Our simplification is no longer a point particle or a particle analysis. So this rigid body is actually where we are making less assumptions about the body itself, and we're considering how force might affect not only the motion of the body, but maybe the rotation, or I guess not only translational motion, but also rotational motion. Now what this does is kind of like where we had in statics, because it is similar, not obviously exactly the same, because now we're looking at bodies that are accelerating. Whereas in statics, we were looking at bodies that were in equilibrium. If we recall when we were looking at statics, that if we had a point particle, we could sum up the forces and they equaled zero. Sum of the forces equals zero, right? So if you had some forces acting up on a point particle. And then we moved on to equilibrium of a rigid body. So now you have a body like that. And then you have a force, and then maybe more than one force. And you still had to satisfy for equilibrium, we still had to satisfy the sum of the forces equals zero. But in addition, with a rigid body, you also had to satisfy some of the moments equals zero. And so what happens with the kinetics, which is the interaction or the motion of a body due to a system of forces or a force. When we have a rigid body now, we still have to account for the sum of the forces equals some mass times some acceleration, which is typically in the translational motion of the body. However, we also need to account for any rotational motion. And we do that by saying that sum of the moments is equal to the mass moment of inertia. That's what I stands for. So that's the mass moment of inertia times the angular acceleration of that body. And so we go through the moment through some of the notes here. If we recall from statics, the moment of inertia is the body's resistance to motion, specifically to angular acceleration. And so very much like the mass in the force equals ma equation, sum of the forces equals mass times acceleration. Very much like the mass of a body is its resistance to motion. Well, its moment of inertia, its resistance to angular acceleration. Or I should say, oh, right here, in motion, I meant resistance to acceleration. We recall that the equation for moment of inertia for a mass, a differential mass dm, is the integral of the distance squared that mass is from the axis of rotation over that mass, right? So we integrate. This is just a straight formulation for the moment of inertia. If we look at a small differential mass and we relate mass to volume through density, then we can say that the mass moment, the moment of inertia, or mass moment of inertia, is equal to r squared times the density rho times dv. And now it becomes an integral over the volume, which is purely geometrical, meaning if the density is constant, we can factor that term out, and this purely depends on the geometry of the object. And so we can tabulate, and that's the case, some of the moments of inertia for common geometries have been tabulated at the back of our book. Or I guess maybe I should say simple geometries. But it keeps scrolling down. We'll get, okay. So they've been tabulated, these moments of inertia. We also are going to be using the parallel axis theorem, which is actually a convenient way to get the moments of inertia for simple geometries about different axis. And so the parallel axis theorem says that the moment of inertia of a body about some axis, some general axis, so we don't have a subscript here, but you could say maybe O, whatever axis you want to call it. In this case, it would be something like C prime. Is the moment of inertia about a known axis plus the mass of the object times the distance squared, where the distance squared is the distance, perpendicular distance between the two axes of rotation. And so it's convenient then. Let me provide some context here. Let's say that for a circle, a disk, a thin disk, where we have an axis of rotation that goes through the center of the circle, I'll call it Z. So picture an axis that is going into the page. So it's perpendicular to the disk. We know that the moment of inertia for a disk, a thin disk, is equal to mr squared, where r is the radius of the disk. Right? Well, the parallel axis theorem, what it does is it lets us relate or actually get the moment of inertia about a different axis. Suppose this axis right here at the bottom. I mean, we can call it A. So what if we wanted the moment of inertia about the axis going through point A? Again, it's still perpendicular to this page, so it's going into the page. Well, we can say that the moment of inertia through A equals the moment of inertia through the known axis Z plus, plus, so we know what the moment of inertia through Z is, so we know that quantity, plus mass, the mass of the disk, times the perpendicular distance between the two axes squared. And so in this case, D is the distance between the two axes of rotation, so between A and Z, that would be D, which happens to be, for this example, also the radius of the disk. Let me erase some of this so that it's not in the way. I believe, there we go. Okay, perfect. And so you can see how we can use the parallel axis theorem. It's very convenient, a very easy way to get the moment of inertia for a disk about a different axis. So like right here, this IZ in blue, that's the mass moment of inertia for the disk about the Z axis that is going through the center of the disk into the page. But if I wanted the mass moment of inertia of the disk through point A, which is through the axis going through point A, then I could use the parallel axis theorem to say, okay, well, the moment of inertia through A equals the moment of inertia through Z, which is known. That's why it's convenient. So we know that quantity, plus the mass times the distance squared, D squared, between the two axes, which in this case happens to be R. And so very convenient theorem here. It basically lets us forego integration, especially convenient if we know the moment of inertia for simple geometries. Again, this is tabulated. It's in a table in the back of the book, IZ equals mr squared. And recall that the moment of inertia depends not only on the geometry, but it also depends on what axis you're rotating about. So that's why in the tables for these geometries, you have more than one moment of inertia. They're given multiple axes of rotation. So you got to pick the right one. Finally, the radius of gyration. Radius of gyration is basically the equivalent radius, and this is how I think of it. It's the equivalent radius that you would have if your mass was concentrated a fixed distance from the z-axis. So for example, suppose your disk, we have the disk again, but now I'm going to draw it like, I'm going to attempt to draw this. From like a side, slightly angled view, right? And then we have the axis, in this case, Z, that would go through the middle right here, down through the bottom. Now notice that the mass of the disk is distributed. It's not all a certain fixed distance from the axis of rotation, from IZ. Well, the radius of gyration says, well, what if we just, what radius, how far from this C axis would we have to place a mass, M, of equivalence, so equivalent mass to the disk, meaning they both, this point mass, differential mass, the point right there, has the same mass as the disk. How far would I have to place that? And I'll put here K. How far would I have to place this mass from the axis Z, so that when I get the moment of inertia, IZ, I get the equivalent moment of inertia, the same moment of inertia that I would get from looking at the disk right here. Which, by the way, we know that for the disk, it's mr squared, where r is the radius of the disk. And so right here, if I concentrate the mass a certain fixed distance from the z-axis, what would k have to be? So the question is, what would k be? Such that I'd get the same moment of inertia. This moment of inertia would be equivalent to this moment of inertia for the equivalent masses. And what we do have here is the equation for the radius of gyration. Was the square root of the moment of inertia divided by the mass. This is actually very much like that formula. But this is a little, it's generic, right? It's saying, well, sometimes you're going to be given the radius of gyration. And if you're given the radius of gyration, then you can get the moment of inertia. Now, this is disk is not, it's not a complex geometry, but sometimes the geometries get quite complex, and you're given a radius of gyration. And from that, you can then get the moment of inertia. Okay, this first section, 17.1, has to do with moments of inertia, mass moments of inertia, and calculating those moments of inertia. And so the first example we're looking at here is an example where we have what we call a paraboloid that is formed by revolving the shaded region, which is this area right here, this region. So if we revolve it around the x-axis, we come up with this geometry, right? And the question is to get the radius of gyration, kx. So meaning if you were to take this entire mass for this paraboloid and place the entire mass a distance from x, some distance from x, some kx distance, such that when you get the moment of inertia of that mass, it should give you the same moment of inertia that you would get from actually getting the moment of inertia of this paraboloid. So they would be equivalent moments of inertia. And so the question is, what is this radius of gyration? How far would I have to place that mass from this x-axis so that I can get the equivalent moment of inertia? And so the approach here is to first get the moment of inertia, which does require some integration. If we get the moment of inertia, we divide that by the mass and then take the square root, and we can get the radius of gyration. Now we can take two approaches, at least as prescribed by our textbook. I decided to use the disk method. I feel more comfortable with that one. It's a little easier for me to visualize, but you can also use the shell method. For me, again, the disk method was easier. Now the disk method basically requires that you make these disks. So they're thin disks of differential thickness dx, meaning every disk right here would have a thickness dx. And I am going to use the formula here for moment of inertia that says that the mass moment of inertia about an axis, in this case x, is equal to the density of the disk, which by the way was given, or in this case the paraboloid, times the r squared dv, where dv is the differential volume, r squared is the distance that the volume is from the x-axis, or that the mass, I will say the mass, right? And so my approach here first, the first thing I want to do is, and let me just kind of get rid of some of this stuff right here so that it doesn't get too crazy. My first approach here is to figure out an expression for a differential volume, dV. And the way I do that is I look at the disk and I get its volume. Now for a disk, which is really a cylinder, that's what a disk is. It's a thin cylinder. We know that the area for a circle is pi r squared. And suppose that you had another circle stacked on top of this, and then another circle. This is supposed to represent these circles, okay? And so you would be multiplying the area of one circle times however many you have stacked up, or you can just say, well, whatever the height of this cylinder is, of this disk, whatever the height of this disk is, h, the volume for a disk is pi r squared, the area of what you can call the base, the top base, times the height, times h. And so I take the same approach here for this disk that I've drawn in here, the purple one. Now, again, we have a disk here. Its radius is r, which actually also happens to be the y coordinate right here at this location, at this x location. So the radius is how much you go up, which is also the y value. And so times the thickness of the disk times the height of the disk, that corresponds to that value right there. So if it has a really small thickness, dx, right? And so the dV, the volume of a differential disk, is pi r squared, that's the area of a circle, times the thickness of the disk, dx. Now I know that the radius, r squared, right there, is, well, I know that the radius is the value of y, so I replace r with y, and I have y squared dx. Now conveniently, y squared is expressed as a function of x. Y squared is 50 times x, and so I can replace y squared with 50x, which is good because we're going to actually integrate this with respect to x, right? And so it's best that we have an expression here in terms of x. And so now I have an expression for dV. So when you're working these problems out, start by doing the following. Get an expression for dV. I have one now. Now, at the same time, I can say that the differential mass, and I'm going to use this later because we're going to have to actually get the mass as well, is simply the density times dV, right? Which is just rho times this quantity. So I'm going to use this expression later to calculate the mass because we do need the mass as well. The mass is not given. We're given a density, but to get mass, I'm going to have to integrate this as well. Now, here's where the disk method can be a little tricky. Notice that the disk that I've drawn here, this purple disk, notice that it's not a fixed distance from the x-axis. Now, what I mean by that is in the disk, in the shell method, typically the way it works out is that the differential volume or differential mass is a fixed distance from the x-axis. Right here, it's not. This differential mass is not a fixed distance from the x-axis. What I mean by that, it's not like it's over here. All of it is right there, and I can figure out the distance that it is from the x-axis. That's not the case here. What's true is that this disk, this mass, this volume, is distributed a perpendicular distance from the x-axis, meaning the mass is distributed. And when I say distance, I mean a perpendicular distance. And so what happens is when you're trying to get the moment of inertia of, in this case, a volume that is perpendicular to the axis about which you're trying to get its moment of inertia, in this case x. Notice how the x-axis goes right through the disk. They're perpendicular. Then we need to take a different approach. We're going to say, okay, let's get what's the moment of inertia of a disk, of this differential disk, so dix. What is that? And if we can integrate, and remember that integrating means adding, summing up all these differential elements, meaning if I can then, if I had, for example, another disk right here, and I'm just sketching, right? If I had another disk, and then I had another disk over here, right? And I had an infinite amount of these disks. They would each have their differential mass moment of inertia dix. And then if I sum up all these moments of inertia, this differential moments of inertia, this one, and this one, and I only drew 3, but obviously there would be an infinite amount, then I can get the total moment of inertia for the entire paraboloid. And so that's the approach we take. Now, the reason we take that approach is because for a disk, we know the moment of inertia. It is tabulated. So for a disk, from the table at the back of the book, we know that the moment of inertia for a disk over an axis that goes through it, the x-axis here, we know that it's m times the radius squared. This comes straight from a table in the back of the book. And so that's what we do here. We say, by the way, this is my explanation right here. You can take a minute to read it if you want. I'm not going to read it for you. And again, these notes I've posted. That's what I'm trying to say right here, what I just mentioned. So we know that for a disk, that's the moment of inertia. And I mentioned that we can look at the back of the book or look up a tabulation. And so for a differential mass, which is basically one of these disks that I've drawn, consider the purple one. For a differential mass, we have di of x. And instead of the entire mass of the paraboloid, I'm going to get a differential mass dm. And then the radius, again, the radius happens to be the y value at that location, y squared. And so what we do then is we say, okay, well, that's convenient now because I already have an expression for dm. I have it up here. It's rho pi 50x dx. And then y squared, again, I also have an expression for y squared in terms of x. It's 50x. And I can replace these values, these two, both as in terms of x. And so that's what I've done here. Y squared is 50x, dm is this quantity. And now I can integrate these differential moments of inertia. So all these moments of inertia, remember integrating is summing up the differential elements, or it's also known as getting the area under the curve. And so we integrate with respect to x from x equals 0 to x equals 200 millimeters. Now initially when I was working this out, and this is just obviously full disclosure here, I wanted to revert this, I wanted to change this to meters by dividing by 1,000, and so I was thinking 0.2 meters, from 0 to 0.2 meters. And I was not getting a correct answer. Now the reason why I was not getting a correct answer is because, well, I guess I was thinking, why is this not coming up? Well, I know my steps are right, but when you have this formulation right here, and this is my thinking, when you have this expression, y squared equals 50x, well, x is in millimeters, and so if I was to divide out 1,000, I would have to divide this as well. I would think something like 0.05x. And so right here, this function is for x in millimeters right here. I'm getting all kinds of places, but if I'm going to express x in meters, then I would have to factor out a 1/1000th, because that's the conversion, right, between meters and millimeters, which would effectively make this 0.05. And so if instead of integrating from 0 to 200 millimeters, you integrated from 0 to 0.2 meters, I would think that you would have to factor that value in here and make that 50 divided that by 1,000 to 0.05. In any case, we integrate from 0 to 300 to 200 millimeters. The only expression here that is not a constant is x squared. And so we get x to the power of 3 over 3. We have density. We know pi, obviously. And when we multiply all this out, we get the following for the mass moment of inertia. 10 over 3 rho pi times 10 to the power of 9. Recall that this is millimeters, and then as a matter of fact, we do have here grams, right? Not kilograms. In any case, we're after the radius of gyration, which says that it's the moment of inertia divided by the mass. And remember that we were not given a mass, but we have an expression for a differential mass dm, which is what I then proceeded to do here. I integrate that expression again from x equals 0 to x equals 200 millimeters to get a mass. The only factor here, the only expression that is not a constant is x. And so I integrate that, I get x squared over 2 times all these constants. And for the mass, I get the following in grams, because the units for rho were grams per meter cubed. Finally, I divide the 2 out, and I get radius of gyration of 57.7 millimeters. Now, my understanding here is that if you were to, so suppose that we have, and this is me trying to explain how the radius of gyration works. If you had the x-axis here, and then you have your y-axis, and before you had a paraboloid, so it was that paraboloid that was revolved, then you produced a volume with a density, thus you had a mass. If you were to replace that with, if you were to concentrate that mass, so the same mass, which in this case is up here, right? This is the mass. If you were to concentrate it at some distance from the x-axis, some distance k, such that it produced the same moment of inertia, I'm misspelling some here, inertia. So that happens all the time. So if you were instead to have the mass, that mass concentrated at a point, a distance from the x-axis, how far would you have to place it so that it gave you the same moment of inertia for the paraboloid And the answer is 57.7 millimeters. So if you took that same mass, put it 57.7 millimeters from the x-axis, you'd get the same exact moment of inertia that you get from the paraboloid, which is obviously not a point. The mass is not concentrated a fixed distance from the x-axis. It is distributed. And so that's what the radius of gyration is. Okay, we go to 1710 here. I wanted to include an example where we have to use the parallel axis theorem, and this is it. We have a pendulum which has a 4 kilogram plate, so that's the circular disc, you can think of it. And then we have a 2 kilogram slender rod. And the question is to determine the radius of gyration of the pendulum about the x-axis, perpendicular to the page and passing through point O. And here's point O right there. I put point A there for when I'm working this out, but the axis goes through this point, perpendicular to this page. So we want the moment of inertia of this entire geometry of this mass, including the plate and the rod, about point O. Now, this is where we can use the fact that these two are simple geometries and that they're tabulated. That means they're in a table in the back of a book. If you look at the back of the book, you'll see a slender rod, and they're going to provide some moments of inertia for the rod, and you'll see a disc, a plate, and they'll provide some moments of inertia for the disc, which is what you have here. All we have to do is apply the parallel axis theorem to get the moment of inertia. Now, for the rod, there's multiple moments of inertia that are tabulated, and you have to pick the one that uses the appropriate axis of rotation. And if you have a rod, for example, if you have a rod, you could ask yourself, what's the mass moment of inertia for this rod if I was to rotate it about an axis that goes right here through the center into the page? And it's tabulated. They provide one. Or what if the axis went, instead it went not through the center, but through this bottom portion of the rod. The rod. So what if the axis was down here at O instead of at A? And they're tabulated. And so I picked the correct one because the axis that we're trying to rotate this by is O. You want to pick the one where the axis of rotation is at the end of the slender rod. And that gives us this. Again, straight from a table, no need for integration. For simple geometries, these are tabulated. And I make a note here that the moment of inertia would be different for an axis that's passing through the center of the rod, which is what I meant here by A. And it's also tabulated, but we're not going to use it, right? We want the one that goes through the end of the rod. And so we get a moment of inertia here of 8/3 kilograms meters squared, which is something to note, the units, mass times distance squared, okay? Now for the plate, we do have to use the parallel axis theorem. You see here the circular plate. We know the moment of inertia for an axis that goes through the center. I'll call that IA. It is the mass of the plate times the radius of the plate. Also from a table, so it's tabulated. And I know that, but I don't want the moment of inertia that about that axis that goes in. It goes through point A into the page. I want the moment of inertia for the disk about the axis that goes through point O into the page. And so again, IA is 1/2 mr squared. The parallel axis theorem says that the moment of inertia about some arbitrary axis, in this case IO, equals the moment of inertia about a known axis, in this case IA, plus the mass of the plate times the distance between the two axes squared, meaning how far is the axis that goes through point A, how far is that from the axis that goes through point O? So that this would be the distance. And which is 2 meters plus half of the radius, so 0.5, 2.5. And that's what I then do here. This is the moment of inertia through an axis that goes through point A plus the mass of the plate times the distance between the two axes, 2.5 squared. And so I finally get a moment of inertia for the plate, because this is only the plate, of 25.5 kilograms times meter squared. The question was, what's the radius of gyration? Well, we added the two moments of inertia from the separate geometries. And we divide by the total mass of the plate and the rod. And we get 2.17 meters. Radius of gyration. Notice the units once again, okay? We have kilograms, meters squared, divide by kilograms, the kilograms cancel, and you have meters squared. And when you take the square root, you get just meters. Once again, let me explain here what we mean by this. Suppose you have this axis. I'm going to draw it at a slant, but it goes through point O, right? So that you're looking at it from a sideways view, and then you had your plate here, and then with your disc. And you have this rod and the disc, they have a mass and they have a geometry, and they produce a moment of inertia of 25.5 plus 8/3. Well, what if we were to replace the rod and the plate by an infinitesimally small point that has the same mass of 6 kilograms, that's the combined mass? How far would I have to put this mass from this axis? So that's what K means. How far, such that it produces the same moment of inertia produced by the disc, the plate, and the rod? And the answer is that you'd have to place that mass 2.17 meters away. Final answer. Okay, we'll cut this video here with the moments of inertia. Work on the homework problems. In the next video, I'll start discussing the next sections in chapter 17, which is actually where we start doing some kinetics, analyzing the forces and the motion of rigid bodies.